I'm hoping some of this will be a review for you, especially if you had Math 98. You've talked about absolute value equations and inequalities before, and we've also talked about the basic absolute value function, so this will just be an extension of that. Our objectives in this section are to graph the absolute value of a function and state its domain and range, be able to apply properties of absolute value, solve absolute value equations and inequalities. Now, back up here at the objective number 1, to graph the absolute value of f of x. We've talked about graphing f of x, right? F of x is nothing more than y. So here we're going to look at the graph of the absolute value of y and see what the absolute value does to a particular graph. So for our first objective, let's start by recalling the graph of y is equal to x. Do you remember that is the identity function? And I'm also going to look at y is equal to absolute value of x side by side. That was our basic absolute value function. So the identity function, remember, that means that the x and y values have the same coordinates. So points like 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, negative 2 are on the graph. Okay, just to name a few. Now, whenever we take the absolute value of that function x, what happens? Notice that where the graph was positive, and that is where we had positive y values, the absolute value of that function is the same, right? And that is because, recall that the absolute value of a positive number is that number, right? Do you remember if I have the absolute value of 5, it is simply 5. So the absolute value of something positive is positive. Now what happened where it was negative? That is where the y values were negative. Well, when we took the absolute value of them, they became positive, right? Because what is the absolute value of negative 2? It is positive 2. So instead of negative 2 on the graph of y is equal to x, on the graph of y is equal to absolute value of x, it is negative 2. So the absolute value function makes all the y values non-negative. Would you agree with that? All y values are non-negative. What does non-negative mean? It just means simply positive or 0. Okay? Because let's talk about the domain and range just to review that for a moment. The domain of the identity function, it extends indefinitely from the left to the right, so it's negative infinity to infinity. The range is what's happening bottom up, and it goes indefinitely from the bottom to the top, which is still negative infinity to infinity. Now for the absolute value function, the domain is from left to right, negative infinity to infinity, so the domain was not changed through this, but the range is what? The bottommost point is at 0 to infinity. So the range is affected in taking the absolute value of a function. So we can state it here. The absolute value of a function is always positive or 0, and the way we can define it mathematically is this. The absolute value of f of x, remember absolute value of f of x, we're talking about absolute value of y, is equal to y if y is greater than or equal to 0. But the absolute value of f of x, or absolute value of y, is the opposite of f of x, which is really the opposite of y, if y is less than 0. Now what does that remind you of? Something that we talked about, one of those transformations. The absolute value of f of x is really saying that that is a reflection across the x-axis. So this piece where the y values were negative is reflected. In other words, it's a mirror image through the x-axis. So let's look at an example of how we can draw the graph of y is equal to the absolute value of x squared minus 4. one way that you can start is to look at what does the graph of x squared minus 4 look like, and then let's get the absolute value of that. Let's do it by hand, and then I'm going to show you how the calculator can help you. So let's just say that you were given this even on a test. Here's a graph of y is equal to x squared minus 4. Now if I wanted to draw the graph of the absolute value of that, well, the thing you really need to look at is where it's positive and negative, and only change where it's negative. And again, what I'm talking about where it's negative is where the y values are negative. Remember that y is positive in the first and second quadrants. Y is negative in the third and fourth. So only this piece where the y values are negative will even change when I apply the absolute value to it. Well, how will they change? So let's look at this graph. Let me see some points here. 3, 5. Is on my graph. Negative 3, 5, 2, 0, and negative 2, 0. See, those points are going to be unchanged when I take the absolute value, because the absolute value of something that's positive or 0 stays that positive or 0 value. So the only things that are going to change is where it's negative. Now if you remember, you can just do the reflection across the x-axis, you could get the graph, but we could specifically do this. Look here, when x is negative 1, my original y value is negative 3, but I've got to take the absolute value of that. So the absolute value of negative 3 is 3. So on my graph I should have a negative 1, 3. At 0, my y value is negative 4, but the absolute value of negative 4 is 4. At 1, I was at negative 3, but the absolute value is positive 3. So do you see what's happening here? This piece got reflected across the x-axis. Now what's the domain and range? Well, even of the original function, the domain is negative infinity to infinity. My range of the original was that bottommost y value, which was negative 4, to infinity. Well, of the absolute value of that function, my domain did not change, but the range is now what? From 0 to infinity. Okay? Again, absolute value does what? It makes everything greater than or equal to 0. Now on the calculator, you can enter into y1 absolute value of x squared minus 4. Be careful to put what's in parentheses, or what's inside the absolute value rather, in parentheses. Remember, to get the absolute value, you can press Math, go over to the number menu, and choose option 1 for absolute value, and then type in the x squared minus 4. And you can see here exactly what we just did by hand. And again, and now in this y1 column, it has the absolute value of all of those original y values that we had. So I've given you a couple of examples to look at just from a graphical perspective to draw the graph of absolute value of f of x and state the domain and range. So you might recognize this as a transformation of that x cubed function, and that's exactly what it is. You don't even really need to know specifically, because what I've got to think about is when I take the absolute value of the function, the only thing again I have to consider myself with is where it's negative. Because where it's negative is going to change when I apply the absolute value to it. And how is it going to change? It is going to become positive, or this piece is going to be reflected across the x-axis. Well, specifically, what is this point? 0, negative 1. 1, let's say negative 1, negative 2 is on the graph. Somewhere it's not really that, is it? Negative 2, negative 1, 2, 3. Doesn't matter exactly what that is, just to kind of get the idea. So now whenever we take the absolute value, we're affecting the y values. So 0, negative 1 would become what? Yeah, 0, 1. Negative 2, negative 3, which I don't think it really is, but we'll say it is, that would become negative 2, 3. Okay. So when we reflect it, it's going to look like this. So the absolute value function would be this piece together with the piece that was already positive. Now what's the domain and range? Well, the domain is all reals, right? It extends indefinitely from left to right, but the range is from 0, right, the bottommost point, to infinity. Now let's look at this graph, and I want to find the absolute value of this function. So this is my original f of x. Well, when I take the absolute value of it, again, the only thing I have to concern myself with is this piece right here, right, where it's negative. Well, this piece on the graph was at -3, -5, and then this is a horizontal line, so all those values are at -5. So whenever I apply the absolute value, again, my y values are going to change, reflects across the x-axis to be what? Well, -3, -5 is going to be at -3, +5. Did I say -3? I'm reading wrong. Please forgive me. I have a cold and it's affecting my brain apparently. Okay, this was at 3, -5. And whenever I take the absolute value of that, it becomes at 3, +5. And then we know we have that horizontal piece through the 5. Okay, so this piece reflected should be going through 5. I think I missed up there, but it should be through 5. And then this piece will connect down. Okay? So again, what are you doing? You're reflecting this piece through or across the x-axis. My domain of that absolute value function, now remember where it's positive, I didn't have to change, but that is still a part of my original function. The domain is all reals, and the range, that bottommost point, is 0 to infinity. Now the next objective is really just to get used to some properties of absolute value, and this is in this section in your textbook, but quite honestly you're not really asked to apply these too much, but just for your benefit, do you know that whenever you have a product inside an absolute value, that is equivalent to taking the absolute value of those factors and then multiplying those values together? If you have a quotient, you may apply the absolute value to the numerator and denominator and then divide. We know that the absolute value of A is equal to the absolute value of its opposite, right? Because the absolute value of 5 is equal to the absolute value of -5. And then a triangle inequality that you're really not going to use until you get maybe into some trig classes says the absolute value of A plus the absolute value of B is greater than or equal to the absolute value of A plus B. The key thing here is that I can't just separate those to say this. In other words, if I have a sum inside, it is not the same thing as just applying the absolute value to each of those terms. I actually get an inequality relationship there. Now, I've asked you here to apply some of these properties just to rewrite these expressions. And the key way that you use those properties is if you're trying to figure out what basic function was transformed or how the basic function was transformed. So if you're thinking about the basic function being the absolute value of x, how was absolute value of 2x minus 4 a transformation of that? Well, so what I could do is think about factoring. 2x minus 4 is really 2 times x minus 2. Well, because now I have a factor that's equivalent to the absolute value of 2 times the absolute value of x minus 2. But the absolute value of 2 is 2 times the absolute value of x minus 2. So we would know that this is a vertical stretch by a factor of 2 and a shifting of the absolute value function right 2 units. What about y is equal to absolute value of 1/2 x plus 5? Well, basically the same thing. If you factor out a 1/2, when you divide by 1/2, you're really multiplying by 2. That would leave a 1/2 times x plus 10. So this would be absolute value of 1/2 times the absolute value of x plus 10. But the absolute value of 1/2 is just 1/2 times the absolute value of x plus 10. So this would be a vertical shrink or compression by a factor of 1/2 and is shifting left by 10 units. Now y is equal to absolute value of negative 3x plus 12. We can take out a negative 3 inside that absolute value to be negative 3 times x minus 4. And so we can write this as the absolute value of negative 3 times the absolute value of x minus 4. But we know the absolute value of negative 3 is 3 times the absolute value of x minus 4. Okay? So it gives you a way to express these in the simplest terms so that you can compare it to the basic function to know how the transformation occurs. Now, objective 3 is to solve absolute value equations. Now, I'm going to rely a little bit on your prerequisite knowledge for this class, but do you remember absolute value means distance? And so if I'm trying to find where the absolute value of 2x plus 1 is equal to 5, this really stems from how we relate to 0 on the number line. For a number, okay, even though that's 2x plus 1, that represents some number. For a number to have absolute value of 5 means that the distance from 0 is 5, right? So we can have distance in the right direction and also distance in the left direction. So that means that this expression 2x plus 1 has to be either negative 5 or 5. And therefore we could solve these by subtracting 1 to get 2x is equal to negative 6. So x would be negative 3, or 2x is equal to 4. When we subtract 1 and divide by 2, we get 2. So that solution would be negative 3 and 2. Now remember, you can check, right? I can plug in negative 3. 2 times negative 3 is negative 6, plus 1 is negative 5, but the absolute value of negative 5 is 5. And then we can check with the 2 and see that it checks as well. Absolute value of 6x minus 7 is equal to 0. Well, the only way to have a number to have an absolute value of 0 is if it is 0 units from 0, which would mean that 6x minus 7 has to equal 0. So we would have 6x equals 7, or x would be 7 over 6. Now remember, you can also solve these problems graphically, right? You could do the x-intercept method or the intersection of graph method, but this is a way to solve them analytically. Now, what about absolute value of x minus 5 is equal to negative 4? This would be saying that the distance from 0 is a negative 4 units. But distance, or absolute value, if you remember from what we were doing graphically, is never negative. Sorry, you English majors out there, that's a double negative, but absolute value is always positive or 0. It cannot be negative. And so when we have the absolute value of x minus 5 is equal to negative 4, there is no solution to this. Okay? Because distance is not equal to a negative number. So here are some properties that result from that. To solve an absolute value equation, if we have it in this form, absolute value of x is equal to k, where k is positive, there are two solutions. So we have to set that inner expression either equal to negative k or k. That is the two numbers whose absolute value is k. If we have absolute value of x is equal to k, where k is 0, there's only one solution. That x has to be equal to k, which in this case would be 0. That might be better for me to write there. Okay. If absolute value of x is equal to k, where k is a negative number, then there is no solution. Now, we're going to extend this concept a little bit further. Now, if you had Math 98, you did not talk about equations of this form where you have absolute value equal to absolute value. But we do know something. if we have a statement where absolute value of 5 is equal to absolute value of something, well, that's true in two cases. This inner number certainly could be 5, right? Because the absolute value of 5 is equal to itself. But we could also have that the absolute value of 5 is equal to the absolute value of negative 5, right? We just learned that in one of the properties we talked about. So there are two ways that make this statement true. So if I have absolute value equal to absolute value, it must be that the inner expressions are either equal or they're opposites. And so what we would do is rewrite this into two equations. We would have to say that x plus 4 has to equal 2x minus 1, or x plus 4 has to equal the opposite of 2x minus 1. So notice that one quantity, that x plus 4, stays the same. We write the same expression from the second absolute value or the opposite of that. Okay, we don't change both of these values when we write that second equation involving the opposite. So now if we solve this, we just solve a linear equation to get 4 is equal to x minus 1. So one solution is 5. Or we get that x plus 4 is equal to the opposite of 2x plus 1. So if we add 2x to both sides, we would get, 3x plus 4 is equal to 1. So we can subtract 4 to get 3x equals negative 3, and therefore x is negative 1. Let me clean this up right here for a minute. So our two solutions would be negative 1 and 5. Now, let's talk about how we could do that graphically. To do this graphically, we have one of two methods. We can either set absolute value of x plus 4 equal to the absolute value of 2x minus 1. And we can graph that. And you see that there are two places where those two graphs intersect at, 5 and at negative 1. So that would be a way we can do it graphically. We could also do, so we could say the intersection of graphs method. We could also do the 0 or x-intercept method, where we take the absolute value of x plus 4 and we subtract the absolute value of 2x minus 1. Okay, and then graph. So do you see there we have two zeros at negative 1 and at 5. Okay, so what we could do, we'll just kind of summarize this, we can do the intersection of graphs. And in doing that, we will let y1 equal absolute value of x plus 4 and y2 equal absolute value of 2x minus 1. And the solutions are the x values where the graphs intersect. The other method is the x-intercept or 0 method. In y1, we would enter absolute value of x plus 4 minus absolute value of 2x minus 1, and then just find the zeros of that function. Okay. Now, the last objective is to solve absolute value inequalities. So let's start by looking at absolute value of 2x plus 1 is greater than 5. Now, do you remember that we talked about just a moment ago the absolute value of 2x plus 1 is equal to 5, and we found two solutions to that. what did we find as our solutions? We found negative 3 and 2. And that's actually confirmed here on the graph because negative 3 and 2 is where those two graphs intersect one another. Those are the solutions. Well, it's equal at negative 3 and 2. So that means for every other value of x, it's not equal to 5 there. It would either be greater than 5 or less than 5. And so we can actually use the graphing calculator to help us know where it's greater than 5 or less than 5. Well, if this is equal to 5 here, where is it greater than 5? Well, if it's above that line, y is greater than 5. If it's below that line, y is less than 5. Well, notice that on my graph, there's two regions where it is above, over here and here. And we've solved inequalities graphically before, right? So it would be greater than 5, where? To the right of 2 and to the left of negative 3. Now, strictly greater than means I cannot include where it's equal to 5. So my interval for this would be from negative infinity to negative 3 union 2 to infinity, right? Because of the greater than, strict greater than, I cannot include those endpoints. So this is a way to do it graphically. If you wanted to do it algebraically, you could test points. Do you remember that? Like if you think about negative 3 and 2 as being numbers on the number line, and then test a point from each region in the original inequality to see where I get a solution or non-solution. Another way you can do this is actually using a compound inequality. For the absolute value of a number to be larger than 5 means that that quantity has to be greater than 5, or it has to be less than a negative 5. So you could solve that compound inequality and come up with a solution. Personally, I think if you know the solutions, then you can use a graph to see how those relate to each other to get the solution of the inequality. Now, another method that we talked about in an earlier section is to look at where it's greater than 0. So a thing that's equivalent to this inequality is this, that the absolute value of 2x plus 1 minus 5 is greater than 0. So remember how we can input this into y1 and then find where it's greater than 0. We know y is equal to 0 on the x-axis. It's greater than 0 above the x-axis and less below. So where is it above the x-axis? Well, that's here or here, which is exactly what we did up here with the intersection of graphs. So at 2 and to the right and at less than negative 3. So we would get the same result in either case. Looking at one of the special cases, where is absolute value of x minus 5 less than or equal to negative 4? Well, if you think about, first of all, where it's equal to negative 4, we found that it was nowhere equal to negative 4. So that means it's going to be either everywhere greater than negative 4 or everywhere less than negative 4. So what we can do is look at the graphing calculator to help us know that. If we input absolute value of x minus 5 into y1 and negative 4 into y2, and we're trying to find where this graph is less than negative 4. In other words, where is the absolute value graph below the line y is equal to negative 4? Well, if you see, here's the line y is equal to negative 4, but the absolute value is all above it. It's nowhere below it. So that means that there's no solution to this inequality. Okay. I could also look at this. When I solve this problem, absolute value of x minus 5 less than or equal to negative 4, if I set that one side to 0, I would get absolute value of x minus 5 plus 4 is less than or equal to 0. So if I input this into y1 and graph it, I'm trying to find where it is below the x-axis. But again, we see it's nowhere below the x-axis, so that tells us the empty set. Now, if that inequality sign had been greater than, notice it's all above, all greater than that. So in that case, it would be all real numbers. So just be careful with the sign. Just because there's no solution to that associated equation does not mean that there's going to be no solution to the inequality. And one last problem to look at where we have absolute value of 3x plus 1 is greater than or equal to the absolute value of 2x minus 7. To solve a problem like this, I would not expect you to go through all this step by hand. You would first find where is it equal. Though you could do it by hand, basically by finding the solutions and then testing points in different regions. But to do it by hand, I would have to say that 3x plus 1 has to equal 2x minus 7, or 3x plus 1 is equal to the opposite of 2x minus 7. So that happens where when I subtract 2x, I get x. When I subtract 1, I get negative 8. The other equation becomes 3x plus 1 is equal to negative 2x plus 7. So in this case, we would add the 2x to get 5x. Subtracting 1 gives us 6. So x would be equal to 6/5. Now, what do those points tell us? If we input 1 into y1 and 1 into y2, and I've darkened the second one, where those intersect are those x values that I just found, right at negative 8 and at 6/5. And then I'm trying to find where is the lighter one, or the normal graph, greater than that bold graph. So where is the normal greater than the bold? Okay, greater than means above. So where does that happen? Well, it happens to the left of this negative 8, right? And to the right of the 6/5, right? Because that normal graph is above the bold graph in those places. So my solution would be from negative infinity to negative 8. Now I can use a bracket because I can include where it's equal to that. Union, bracket at 6/5 to infinity. Now you could also do the x-intercept or 0 method. If you set one side to 0 by subtracting the absolute value of 2x minus 7, which is what I have here, we're trying to find where the absolute value of 3x plus 1 minus the absolute value of 2x minus 7 is greater than or equal to 0. So that means I'm trying to find the regions where this is above the x-axis. And it is above to the right of that 6/5 and to the left of that negative 8. Okay? That concludes this lesson. If you have any questions, please don't hesitate to contact me. Thanks and have a great day.